As we know, the operating system manages memory. When the computer loads, the operating system is loaded into RAM, as are the programs that we're currently working on. It's important that no two programs can access each other's data. Why do you think that is? Pause the video and try and answer that question. The reason that we don't want different programs to access each other's data is because this would open us up to malicious data attacks. Another role of the operating system is to ensure that the free space on RAM is being used efficiently. When a program closes, it actually relinquishes its space in memory. In our abstracted view, we have closed Python, and you can now see there's a space in the RAM. This is now free space. It could be used by another program. If a program is small enough to fit in that space, it could move straight in and open and start running. However, here in this instance, Microsoft Word is trying to open. There is enough memory in RAM because we have two spaces above Spotify, but there's not enough memory in one place for Word. So we're going to have to think about our memory management. It would seem that the easy solution would be just to move Spotify in memory, so that Word would have enough space so it could be contiguous in memory. However, this is not a very good solution for the computer and for RAM. That's because it would take a significant amount of time to move the memory and to move Spotify around. Not only are we having to shuffle the data, but we're having to shuffle the addresses and free space references, and these would all need to be updated. We need a more productive way of doing this, and let's have a look at the two ways we could do this. Our two options are paging and segmentation. Each of these two involves splitting the memory into smaller sections. Remember that we only use paging and segmentation when there's insufficient memory for a program to be contiguous in RAM. If it can be contiguous, then it will be put straight into the space in RAM. Paging is when we split the memory into fixed size pages. Each page represents a small amount of memory and usually 4 kilobytes in size. You can see from our abstracted view that this is what we have been looking at so far. Each of these small boxes on the right hand side would represent 4 kilobytes. However, when we're using paging, we split a program up into non-contiguous pages. So in this instance, we could have 2 of those pages which are stored above Spotify. The rest of them could be stored below Spotify. So if a program is using 15 kilobytes of consecutive memory addresses, then it might be stored in 4 separate pages within our memory space. We use a page table to map and store a link between the physical memory addresses and the logical address space of each process. So in our example here, our 4 pages are split between our 4 memory locations. Page 0 is in 157, page 1 in 162, page 2 in 163, and page 3 in 166. From each page, we'll then have a map or a link to where the next page is stored. So 157 will link to 162, so the computer will know where to go to find the next page of memory. When we first look at paging, this sounds like a fairly simple solution. However, we don't actually look at the code which is being separated. We split this up into small blocks of 4 kilobytes of memory. What would happen if we were in the middle of a loop? We'd have to keep moving between different pages, and so this massively lowers the efficiency. The best thing would be to keep the parts of a loop together. So there is another solution. The second solution is segmentation. This solves the issue of logical structures being separated. We can divide a program into logical divisions instead of fixed size pages. Think of these like modules, functions in our programming, or it might be a loop in one segment. These logical divisions depend on the program structure, and that means that the sizes of these will vary. As with paging, it's possible to only load part of the program into memory initially. Let's take a look at the similarities and differences between the two. So the similarities are that both allow programs to run despite insufficient memory. That's only when we actually have enough memory in RAM for part of the program that we need, but it's not contiguous. So it's non-contiguous, it's not in one space. If RAM was full, we'd have to use virtual memory. Now remember, pages and segments of program are stored on our secondary storage until they're needed, when they are transferred into our RAM. The differences, though, are pages are fixed sizes, where segments are different sizes, quite often logical structures. Pages are made to fit into sections of memory, whereas segments are complete sections of programs. And pages are physical divisions within our RAM, where segments are logical divisions.
So we've been used to using static arrays to store data. Remember, when we want to create a larger array, what we have to do is we have to make a new array. An array is a static data element. We can't make an array longer once we've set it. So, to do that, we'd have to create a new array somewhere else in memory. This can be quite memory intensive because we've got to move all the data values from the initial array to a new array after we've created it. Well, there is another way that we can work around this, and this is known as a linked list. A linked list, instead of storing data in memory contiguously, so in one block, it stores data wherever memory space is available and links them together with pointers. This enables data to be added, inserted and deleted with ease. It's just the pointers that need to be updated. So a linked list is made up of nodes which contain two items: the data item and the next address, or the link item. So these nodes make up a linked list. So this is actually an example of a linked list in a data structure. Each node, remember, is held in one part of memory. It has its data and its link. Now, to make sure this is correct, each node is given an index, and the order of the nodes can be worked out. So we know that index 0 is first. It's actually alphabetical order, this. The starting node, aardvark, points to the third node, badger, which is at a different place in memory. We are looking at them here sequentially, but remember that it's unlikely to look like this in memory. Badger points to elephant, and elephant points to vulture. The pointer 0 means it's the end of the list. This is fairly simple to set up initially, but actually adding and deleting items from a linked list can be more challenging. But because they're not stored contiguously, we only need to update the links, the pointers. So we don't need to worry about moving data and shuffling data around. This is a way that we can actually get around expanding arrays. If we wanted to delete the third item, so our third item in our list is badger, we'd have to update our pointers. Now the pointer from aardvark goes to badger, so we need to update pointer number 3 to pointer number 2. The rest of the list can continue, isolating this data value. Notice how this data value has not been removed from memory. We just changed the pointers. Now the computer would know that this value could be overwritten in the future, but the value is still there, and this is why sometimes we can retrieve data. Another massive advantage is that if we want to reorder a list or order it in a different way, we could just add a second set of pointers. So we could decide blue was alphabetical order and red was size order, and we can just put a second set of pointers within our. So to insert data, what we're going to actually have to do is change the pointers. We did this for deleting data, and it's exactly the same for adding data. There's almost certainly likely to be free memory in somewhere. So basically, we just need to make sure that the pointer is pointing to the next free node and add the data to that node. And then adding it at the end means that all we need to do is update the last pointer to 0, or the pointer and the last value to 0, and the last data value which was before to the new data value. First of all, let's have a quick look at how we could list out the values in a linked list. We're going to use iteration here. And we're going to say while the current pointer does not equal null, so while it is not 0, it's going to read the data and move to the next pointer. Now it's very hard to actually do this in Python because Python uses lists. So we'd actually have to store it in a general array to see how this would work. But in some other languages, it will work significantly different. You can see here we've got a search algorithm. We have a current head, so like the first value. Found equals false, so it's going to continue through our iterative loop until found is true. Can you see how we're using pseudocode here? While the current item is not found, it's going to keep looping through this iteration. If our current value .getData is equal to the value that we're looking for, we can set it to true and exit the loop. Otherwise, it's going to move on to the next value until it's found it. Now notice this is in a function, so it returns the value at the end. Now to insert a data value, remember we're going to just add this right at the end. So first of all, we need to find where the next free node is. So we're going to add our data into the next free node. Now remember, in Python this works slightly differently, so we have to structure this in a different manner. We've got linked list new node.data equals new item. We set the pointer to 0 for this item. You can see that now we can actually transverse the list, updating the pointer by 1 each time until the item in the list is greater than the new item. We can change the node before the insertion place if we want to insert it into a certain position, and then change all the values after it if we want to add it partway through our list. Now here's an example of deleting that value badger from our list. Now the first thing we're going to have to do is figure out which position is going to be deleted. And we know it's not at the end of the list because badger's pointer is not 0. If it was at the end of the list, then that would actually be quite simple. We could just delete that value, but we'd have to loop through our list until we found the n-1 value and update its pointer to 0. And that would remove it from the list. In this case, it's not at the end of the list. So, first of all, we could set the pointer to 0. We transverse the list, updating the pointer by 1 each time until we reach the item which is going to be deleted. So, iterating round the loop, round the data items, until we find that item to delete. When we've found the item to delete, we need to change the node before it. So the pointer of the value before that needs to go to the pointer of the value after it. So we can then delete that node and we freed up that position in memory.